that much, to be honest. Okay, so for people who are like watching this recording, like I missed recording the class until now. So till now we've basically discussed this sort of warm-up problem, which is also available in one of my previous lectures, I think the one on processes. So you can watch it there if you want. And we spoke a little bit what Olympiad combinatorics is. So yes, counting and n factorial, etc. forms like a major part of it, but um there's also a lot more. And today's class is mostly about, thinking outside the box and coming up with these interesting and innovative ideas, which really makes me feel that um, combinatorics is really very enjoyable because of such ideas. So today's class is going to be about how you can come up with such ideas, and in particular, how can we make our box bigger so that stuff which even feels out of the box is sort of inside our box in some sense. So
Sir, can you show the previous questions? I can take a
yes,
screenshot.
yes, yes. I'm back here. So yeah, the problem we're currently trying is this. This is from the ARMO SL, and
No, no, I
yeah,
am talking about the question that you forgot to record.
this one.
Yes, yes.
Okay, you can take a screenshot.
Okay, all right, thank you.
Okay. Okay. Also, I think it's like time we start discussing. So, does anyone have like any idea whatsoever? Like, just um, basis like first thoughts.
I
First,
tried out I tried out small values of n, like for n equaling 3, I just tried that I move each stone the maximum that they can. That satisfies, but it fails at n equal 5. Then I was thinking that we can label the stones like we did in the previous problems from n to 1, like from 1 to n. And
okay, 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 okay. It's okay, it's okay. You're getting somewhere, but let's not go too fast with this. So first thoughts is that n equal 3, n equal 5. What do those sorts of things give? So it's quite interesting actually because like for example, like let's try and figure out where this n by n is coming from. This is just one, by the way. So like for example, okay, let's just look at 7 stones. So it's kind of intuitive that this top stone can be moved by 7 and just reach the final destination. So it's kind of contributing this n by n to us, like just one move for getting this here. And in some sense, like maybe then what you want to think is that maybe the bottom stone is what will contribute the n by 1 in some sense. Now, it's still going to be very unclear. But let's think about it, right? So let's imagine the situation where there is only one stone left in the first pile. Like all others have been moved by some distances. So there's only one stone left. So of course this has to be moved by one right now. Now, if again this second pile was empty when it joined the second pile, or rather pile one, because this is pile zero, um, then again it'll have to move by at most one. And again, if this one was empty, then it again would have to move by at most one. The problem comes in that what if this pile already had a stone? So now when you moved it here, now you can move it by two. So ideally you would want that this bottom stone is moving in like steps of at least at most one. But that's not really working out very well right now. But okay, like I mean, it comes here and there are two stones in this pile, and okay, sure, it moves by two. But there is still this one below it, right? Like the one below it still has to move by one. So in some sense, like at every point you can keep looking at this sort of bottom one and it sort of moves by one, and that kind of leads you to the n by one term. But it's still very weird because like we're changing which stone we're looking at a lot. which is why if you start labeling them like with 1 to n, etc., it's going to get very annoying because like ideally you would want something like, pile 1 moves in steps of at most 1, sorry, stone 1 moves in steps of at most 1, stone n moves in steps of at most n, etc. And then we would just be done with the problem. Of course, it's not that easy. Um, but let's think, right? Like, okay, so this is sort of some n by 1 something. What if there are 2 stones in the first pile? Then that stone hopefully moves in steps of at most 2. So if you think of that second stone from the bottom, now it's going to move by at most 2. Then if there are like 10 stones currently in this pile, and now you created an 11th stone in this pile, now eventually there will be only 2 stones in this pile, at which point that stone again will have to move by at most 2. And then again by at most 2. So this is kind of leading us to the sort of bound we need. But it's weird because, maybe like we already counted this move when we were looking at that n by 1 thingy. Like, how do you know you're not counting the same move for 2 different people? Like, like it's very messy, right? Like, how are you supposed to write something like this formally and like, what exactly are you even doing? So that's the question. Um, Someone has given us an idea. I got to the point that each square has 1 stone first in n moves. Okay, so that's another idea. You can move everything by 1 and get to this. And here's the thing, right? Like we can do a lot of things and we can get some constructions, right? Like we can get, um, for example, let's say we can prove that in square terms or like in n log n terms, something like that, I can get everything here. But that doesn't solve the problem. What we need to show is that it needs to take at least these many. So trying out to like construct out of some example is good for intuition, yes, but it'll not help you get too close to solving the problem here. If they had asked us to show something like at most, then for sure you need to try something like that. Because then you need to construct some sort of way in which in at most these many terms you can reach 7. But here you need to more think about how I can show that it'll take at least these many turns, even though like I really don't know what's going on. Um, so um, that's a little bit of um what's going on. But let's think again, right? Like we had this sort of n by 1, n by 2, something something, not very clear, like very vague, right? Like a slightly maybe more okay, someone has sent a message on chat. We can move the top stone between anywhere from 1 to n. Similarly, when placed anywhere, the next stone can be from 1 to n minus 1. We can do this at the end for the last stone. We place all the stones on the position which will be furthest, so n stone, etc. And similarly, we might get the answer. Okay, so this is what the other person was also suggesting. So you move the first, like keep moving by like sort of the max thing. And again, the idea I want to reiterate is that this is a very good idea if you want to show at most these many moves. If you want to construct an example on when you can reach in like a fixed number of moves, like if you only have 100 moves, at most 100 moves make, you have to reach there. Then it's all a very good idea. But if you need to show at least 100 moves, now there's no point trying to find a way to do it in 100 moves. Instead, you need to look at how you can show that 99 moves is just not possible. So, like, if you are trying to show that by my method, 99 moves is not possible, that doesn't prove anything, right? You need to show that if you use any method whatsoever, it'll still not be good enough to do it in 99 moves. Like, okay, 99 is an example, but you get the idea. Um, but let's go back to this sort of oh, I stopped sharing. I'm so sorry. I clicked the wrong button. Um, yeah. Uh, okay. So yeah, so let's look again at that n by 1, n by 2 thingy. So the pile that is at the stone that is at the bottom of a pile, it will move by at most 1. And now again, this new pile, like the one next to it, will eventually have a bottom stone, and that'll move by at most 1. And then this will have a bottom stone, something like this. That's sort of the intuition by which we're going to go along. The issue is, of course, that ideally, we would want to say that this bottom one, let's say we label this as 1. This stone 1 is the one which is making all of these moves. Instead, what you're saying is that after it comes here, now look at the new bottom one, which might be stone 3. Now that stone 3 on the next turn might become stone 5. Like, that's annoying at all. Very annoying. But here comes the magic trick. Um, we label the stones, right? Like all the stones look the same to us. That's the point. That's the same idea as what we did in the ants. But it's kind of the reverse. Like there, you want to like not differentiate them. Here, you want to sort of differentiate them in a weird way. So instead of placing the stone 1 at the top, what if you just place it at the bottom? Like now, eventually, this same stone 1, which is at the bottom of the pile, will move to the bottom of the next pile, which will then move to the bottom of the next pile, and so on. So this stone 1 is actually going to move in steps of at most 1, and that's very good. And similarly, okay, n definitely works out, right? N just gives you at least 1 move is needed for it. And okay, I don't want to cause confusion. So what we actually have to prove is that at least these many turns we need. So that's interesting. So we've kind of broken a rule that, okay, the problem set kind of like you have to place it at the top of the new pile, but I don't care. I'll place it at the bottom of the new pile. Like, who cares, right? I mean, the only thing that is defines the configuration is the number of stones in the pile. It doesn't matter in which way I order them, surely. So that's cool. Now, what happens to the second one, right? Second one is here. And again, I don't want to place at the top of the pile because then again I'll cause confusion. I don't want to place it at the bottom because that place is kind of reserved for the first turn. So what if I place it at the second position? So we don't actually know actually if 1 is going to be here. So maybe currently there is a little bit of like lack of clarity still on like how you want to do things. So um, what you want ideally though is that the stone 2 moves in steps of at most 2. So it's okay if it makes a move of 1, but it's not okay if it makes a move of 3. Does that make some sense? Somewhat?
Mhm.
Eventually, stone 1 will come below stone 2. Stone 1 is always below stone 2 by the way we have now defined it. We're just placing it at the bottom of each pile. So there is no way. Okay, yes. You're saying that if currently there is no stone 1 in this pile, like maybe later on we move stone 1 and then we push it below. That's okay. But yeah, that's interesting. So maybe what you're saying then is that okay, if there is no stone 1 in this pile currently, like right now there is 3 or something at the bottom, I'll just place 2 at the bottom. Then later on, if 1 comes in, I'll put that below. If it doesn't come in for now, it comes in later on, then it's okay. We'll deal with it later on. But the point is that 2 is either going to be at the bottom or it's going to be at 1 from the bottom. So there'll be at most one thing below it because that's stone 1. Like we're just always going to put 2 at the bottom unless 1 is at the bottom, in which case we'll put it at second from the bottom. In a more concrete sense, basically what we're going to do is we're going to make sure that each pile is sorted. So the bottom stone of the pile will be the smallest number, and the top stone of the pile will be the largest number. So for example, if a pile currently has like 3, 5, 8, and you want to move in 4 into it, you'll push it in this gap. So what this ensures is that when you have stone 4, there are at most 3 stones below it at every point. So stone 4 can move in steps of at most 4 because if 4 is at the top of the pile, then that means that there are at most 4 stones in the pile because there can be nothing above it. So only things that can be are 3 to 1. So now what you're saying exactly is that stone 4 will move in steps of at most 4. So there you get the n by 4 term, or rather the other, sorry, not floor, it's ceiling. Ignore the floor and ceiling, that is not really the crux of this problem, but um, the main idea is that, you know, things weren't really exactly working out exactly very well because, you know, we were switching which one we were looking at. There was a lot of confusion because the problem didn't kind of give us enough data. Like it gave us a lot of stones, but it didn't like label them or it didn't help us understand which stone is which. So we give it this sort of artificial structure, which is that, you're pushing it in between so that things are sorted and you're labeling the stones. Which is this sort of very innovative idea. Like, I mean, no one asked you to label the stones. Like, they literally told you that they're n identical stones. But you still said, no, I will make them distinct. I will label this one 1, this one 2, this one 3 till n. Like, I don't care if you make them, you announce them as identical. That's kind of opposite of here. Like, even if they told you the 10 ants look very different from each other, like, the point is still, okay, I don't care. They're at the end of the day, they're ants. So this is sort of the whole idea here, where it's kind of like breaking a rule in a sort of a legal way. So of course, you're not like changing the problem or like solving your own problem. Like, okay, their problem is too hard. I will try my own problem and I will solve it. The problem is still equivalent, but you've come up with this sort of very interesting idea, which sort of originates from this whole question about structure. So, a more concrete way of thinking about when you want to do something like this is when you feel that there is a lack of structure in the problem. You're not able to understand how things are going on. Like, there was a lot of confusion in our mind. Okay, where is it going, what is going on, which stone is going where. There's a lot of confusion. So you give it this sort of extra structure to make your job a little easier. What if we relabel at every step? That is also equally valid. Like, what you're just saying is that, okay, put it at the top, but then again switch the label so that it becomes sorted order. Like, that's kind of the same thing, right? It's just these are just two different ways of thinking about the same thing. The main idea in each case is that you want to think of the fact that you want to label these terms and you want to label them in a way that things work out nicely. Um, so yeah, I think it'll be even more clear when we do this other problem, which is going to be also quite cool. This is from IMO 2021, I think, P5. And I think this is, I think, one of the coolest combi problems in the last few IMOs, apart from maybe the one last year, which was also very cool. Um, but yeah, so we'll again come back to this problem, by the way. So if there were some doubts, we can discuss it again. But I just want to show you some sort of a little bit of uh okay, I don't want to spoil too much, but yeah, this problem is interesting. It's like you have walnuts. This time they're labeled, by the way. So they're 1 to 2021, and there are some circles. So again, this feels kind of like counting, but as you'll see, like combinatorics is so much more than just counting. Like, yes, like you have like these circles and you're permuting things, but the point is not to count things, it is to solve this sort of process. Um, anyway, so you have like these 2021 circular holes around a tree. The favorite tree. That's not very important problem. Um, and they're they're labeled in some sort of weird way. So, for example, okay, so you also have 2021 walnuts, which are like 1, 2, 3 till 2021. Um, and I can place, for example, in the first hole, I can place the third walnut. In the second hole, I can place the fifth walnut. In the third hole, I can place the 2021st walnut, etc. So, um, yeah. So now this has uh, each morning, Jumpy notices that Bushy has placed one walnut into each hole, but had paid no attention to the numbering. So they have done it in a random order. Unhappy, Jumpy decides to reorder the walnuts by performing a sequence of 2021 moves. In the kth move, Jumpy swaps the positions of the two walnuts adjacent to walnut K. So, for example, if walnut 1 is over here, um, then let's say 2021 and 7 are next to it. So what this Jumpy will do is it'll switch 7 and 2021. And it'll keep doing this. So first it does it with walnut 1. Then maybe if walnut 2 is here, then it'll switch this one with this one. Of course, there are a lot of dots here, so whatever. But the point is that you look at, forget, there is no like labeling of the holes, by the way. Like, you're just looking at the walnuts where each walnut is. So you look at walnut number 7, flip the neighbors of 7, and keep doing this until you reach 2021, and then you flip the neighbors of 2021. Um, and you have to prove this very interesting statement that at some point when you are flipping, let's say you're flipping 5, then the two things you're flipping, one will be bigger and one will be smaller and one will be bigger. So you will have like 3 is less than 5 is less than 2021. Um, so yeah, very weird statement. Like, wow, like how are you supposed to even approach something like this? You have no idea how they were like initially positioned. Like they could be done in order, they could have been done in reverse order, they could have done in random order, like anyhow. You have to show that no matter how they were randomly organized, and these 2021 moves are done in this order, um, you can do the problem. So yeah. So the first obvious thing is that 2021, of course, is totally random. Like you can replace it with, let's actually think what happens when you try replacing 2021 with a smaller number. So obviously for n less equal 3, it doesn't make sense because, I mean, you need to have two neighbors. So let's try n equal 3. So you only have like three things and 1, 2, 3. Um, is it reordered by 2021 moves? Um, I didn't understand. So yes, when you're flipping things, there is change in this new ordering, but there is no guarantee that after 2021 moves, the final position is going to be sorted or something. Like you have no idea how it'll start, how it'll end. All you have to show is that in between you go through this. So anyway, let's try and yeah, we can try and use contradiction. That's interesting. So at every point, assume that either both are bigger or both are smaller. But even before that, let's try and figure out what happens when n is 3 or n is 4, something like that. So let's say we have 1, 2, 3. So first, I mean, also notice that here there is no real concept of a permutation. Like, I mean, however you label them 1, 2, 3, in some order they will be 1 to 3, either cyclic, like either clockwise 1 to 3 or counterclockwise 1 to 3. Like you just can't change that. But okay, sure. Let's say 1 is first flipped, so now 2 and 3 get flipped, then 2 is flipped. And okay, when 2 is flipped, so first of all these will change, and now 2's neighbors are 1 and 3, so yes, a is less than k is less than b, and so you're like done. That was like a very trivial case, like not very fun. um the interesting thing is what you notice when n is equal to 4. So, in fact, consider this scenario. So, 1, 2, um, wait, yeah, 1, 2, 4, 3. Let's try this. So, first 1 is operated on. So, 2 and 3 get flipped. So, now your new situation is something like 1, 3, 2, 4. Now, 2 is your start point. So, you flip 1 and 4. So, again, oh, wait, no, no, no. Now you've already done 1 less than 2 less than 4. So that's very nice. So actually, I was trying to look at something else then. Um, let's try something else. What about 1, 2, 3, 4? No, not this either.
Yeah, I
Uh,
think the counterexample is like small numbers in even positions and
yes, yes, yes.
large
3,
numbers
4,
in
and
the odd.
1, 2. Yes, yes, yes. That makes a lot more sense. Thank you. Um, Yeah, so you have like 1, 2, and 3, 4. Yes. So first 1 is flipped. So 3 and 4 get exchanged. Then 2 is flipped. So again 3 and 4 get exchanged. Both of the numbers were bigger. So like this didn't work. And now again you're back to the same thing because you flipped these two twice. So okay, just to write it down, like first you flipped 1. So you got 1, 4, 3, 2. And again you did at 2. So you got again 1, 3, 4, 2. Now you do it at 3. So 1, 2 get flipped. So 2, 3, 1, 4, and then you do it at 4, so you get, so at each point both the numbers were either bigger or smaller, so that's actually like crazy, like you kind of disprove the problem, but it's for n equal 4. So what it suggests is because it worked for 3 and it's a guess, but it worked for 3, it didn't work for 4, and apparently it works for 2021. So the guess is that maybe it works for only odds, as someone is saying. Exactly. So yeah, for evens, in fact, you can construct a counter example, which is like, as Anandu said, like put all the big numbers on even positions and small numbers on odd positions. Um, and then it'll turn out that you never actually solved, you got this sort of situation. So in some place, we will have to use the fact that 2021 is odd. But apart from that, it's probably unlikely that we will use the fact that 2021 is a number at all. Like it could have been any odd number, probably. But okay, let's forget about that stuff now. Let's actually think about what to do. We could contradict by considering k less than a less than b. Yeah, so I mean, we can assume that at every point, either both the numbers are smaller or both the numbers are bigger, the neighbors. Yes. So let's actually assume this, that every point you are either flipping to numbers that are both bigger or are both smaller. So the question actually right now is that, I mean, if you've gone for this sort of contradiction, and let's say like k is like 7, and 7 is greater than both 1 and 2. 7 is also greater than both 2 and 3. It's also greater than both 5 and 6. Like, as long as a and b are in 1 comma 6, we don't really care which ones they are. Does that make some sort of intuitive sense? Like, um, 1, 2, 3, 4 till 6 are sort of the same thing for you. And similarly, 8 to 2021 are the same thing. Like, only thing you care is that either both numbers should be from this set or both numbers should be from this set when k is 7. And then after this move, k will become 8. So then you will have to add 7 into this set and remove 8 because 8 is the number in question. And in some sense, you want to keep checking that both the numbers should be in the same set in some sense. You don't really care whether they were 1 and 2 or 6 and 7, etc. You just care that they're of the same type. Does that make some sort of sense?
Yes.
Okay, so let's actually label this. Let's color 1, 2, 3, 4 till 6 um as red, and we'll color the other numbers as blue. So our condition is basically saying that when we're working on 7, then you're hoping that either both the numbers are red, the neighbors, or both the neighbors are blue. That's what we're saying. Um, and what happens after this turn is that 7 becomes red because 7 becomes a part of this set. So let's think of it again. So you have these numbers. On the first turn, you have all the numbers are blue except 1, which is the number in question. So it doesn't really have a color. But let's imagine that 1 is red. Let's say it doesn't really matter. So let's say 1 is red. And right now, all of its neighbors will be blue because all other numbers are blue. So that's cool. So both these numbers were blue. And now what happens is that after this, um, this is red. So now, for example, if 2 was over here, now 2 will become red, but then 2 will have one red neighbor and one blue neighbor because this number is by definition blue. Something like this. So basically, it's like numbers are becoming like initially everything is blue and slowly some numbers are becoming red. And you want that at every point, um, each number is that you're looking at that has both of the same type. That's sort of some sort of intuition. We still have to formalize things, right? But this is very interesting because what we have done is that once we've reached 7, we don't care about what number was 1, what number was 2, what number was 3. All of them are just red. So we've lost a lot of structure. And I think, okay, maybe it would have been better if, if, of course, in an ideal scenario, like people have spent 2 hours thinking about this problem, because what you'll realize is that there is so much structure in this problem. Like there is so many numbers, like so many different things you can try. Like there is so much data that it's very hard to control things. The other problem like it's very hard to control things, but for a very different reason, because you just don't know what is going on. Here, you know too much. So it's like I am purposely trying to like put my mind out of some sort of things because I feel like, okay, maybe they're not as important right now. So I'm going to look at only a few things. Okay, someone has asked a doubt. We know that 2021 is the biggest number, so wouldn't the condition? No, so when 2021 is being operated on, both numbers will be smaller than it. So we didn't break the condition. Like we need either both number, like we need one number to be bigger and one number to be smaller. Then we would have solved the problem. So we have assumed for the sake of contradiction at each time both numbers are smaller, both numbers are bigger. So in fact, we will never break the condition at 2021. So like it'll always have to happen before 2021 if it ever happens. So let's think about this again. So you have a lot of numbers which are blue. All numbers are blue. Blue, 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 blue. They're all the same. I don't care. There was 1 to 2021, doesn't matter. So now I'm going to the one which was one, but I don't really know which one was one because all of them just look blue to me. So okay, let's say this one was one. I don't know for sure, but let's say. And okay, of course, both of its neighbors are blue right now, so that's all cool. I can make it red. So this number changes from blue to red. Now we know that uh, this number cannot be two, because if this number was two, then it has one neighbor red, one neighbor blue, and that would create some sort of contradiction, right? So what you will need is first this number must have to eventually become red, and then you can make this number red. So by the way, the objective of this new sort of intuitive game is that you want to make all the numbers red. Like all numbers start off as blue, and slowly you're performing moves which make more and more numbers red. And the only condition at each point is that whenever you're making a number red, that is that you're operating on that number, um, both of its neighbors should be of the same color. And okay, one other thing, by the way, is that when we operated on this number one, we actually flipped these two. We flipped this and this because that is what the problem said. But because both of them are blue, like even when you flip blue and blue, they still look blue and blue. It's the same idea as the ants problem. Like, yes, you flipped them, but doesn't matter. So the only condition now is that at every point you're going to pick a number that is currently blue, and both of its neighbors should be the same color, and you'll make it red. And okay, technically these two will flip, but that doesn't matter because they're the same. Does that make some sense? Like we will think about this more. It's an idea that takes a bit of time to get used to. So you have these numbers, everything is blue. At each point, you pick any number you like, because any number could have been one. We don't know. So we'll just go with every possibility. You pick any number you like, and you change it from blue to red, as long as both of its neighbors were of the same color. And then you do it on another number which is currently blue until all numbers become red. And if all numbers become red, that's actually really bad because then you've disproved the problem. So what you want to show is that you can't make all numbers red, if that makes some sense. So initially, so just to think of this in the n equal, let's say 5 example, you have like 5 blues. And let's say first turn, I choose to make this one red. Now, this blue has both of its neighbors as uh, red currently, as blue currently. So again, I can switch this blue to red. Uh, Now, this blue has both neighbors as red currently. So I can switch this one to red as well. But here we've got stuck because this blue cannot be switched because opposite neighbors, and this blue also cannot be switched because opposite colors. So that's sort of the idea. Does this sort of make sense to people? Like, if there's some doubt, like, please ask now about what we're doing. Like, we still have to prove that we can't finish this, but um, is the whole process clear?
Yes.
Okay. So yeah, now the final part of the problem is to prove that you can't get all reds. That is more of a more standardized like invariant sort of problem. Like you can think about that on your own. You will have to, of course, use the fact that n is odd. We can also discuss it. Like I don't mind discussing it, but it's also a cool question for you to think about. But what I really wanted to bring about across this question is that it's so different from the previous one. Like there, all of them look the same, but you're putting actual numbers to all of them. Here, they literally gave you actual numbers, but you're just thinking of them as reds and blues, and you're like losing so many conditions. Like I forgot which one is one, which one is two. I'm just looking at any number which is blue currently, and I'm just switching its neighbors. In fact, I'm not even switching them because they're the same to me. So you are breaking so many rules in the problem. It shouldn't work, but it does. And that's sort of the magical part about both of these problems
Are you
because,
actually losing information though? Like, aren't these two games equivalent?
um,
Uh, like you
it
can
is,
label
it's a
the,
question. Yeah, I think you're not losing information when you decide that, okay, I will look at every scenario on, yeah, I mean, you're technically not losing information. You are right because you're definitely breaking some rules though, because when you switch these two things which are blue, so
yeah, all blue numbers
uh
are the same.
yeah, so like if you at the end try to like compare each number with what it was in the initial thing, they probably won't
Yeah,
match.
yeah.
Yeah, but in some sense, yes, you're losing information, but
But
also
it's
you're right that
like an equivalency like the ants
yes,
problem.
yes,
Yeah.
of course, it has to be an equivalence, otherwise we wouldn't have like solved the problem.
Mhm.
Um,
No, it may be that
okay,
there's
yeah,
a
you can lose information and
you
still
can
solve a
still solve,
problem,
but
but
in this case, like
sure,
it's equivalent. Yeah.
yes, yes, the two problems are equivalent, but it feels very counterintuitive that you can get away
Yeah, yeah,
with
it
something like
does. Like
this.
this feels a lot simpler.
Yeah, yeah. Like this feels like almost like, I mean, like that, like you first of all lost the condition that you're operating on 1 to 2021 in that order. Like for example, when I'm doing blues and reds here, I could do them in any order. I
Mhm.
could, and I'm again forgetting which ones are flipped, etc., etc. I'm like losing a ton of conditions. But yes, in terms of equivalence, yes, of course the problems are equivalent. But that's the very interesting part that like despite changing the problem completely, like you can still get away with saying that they're equivalent in some sense. Um, and yeah, I think what I want to leave with these two examples is that um, this problem is more about sort of like figuring out how you want to create structure to help you in the right way. This problem is how you want to remove structure so that you can do things in the right way. And I think these sort of things don't come to your mind quite easily, which is what makes them very tricky problems. In fact, I think this one was a P3 on the India TSTs, even though it was like a C3. And this one, of course, was an IMO P5, which didn't get too many solves, although also it wasn't too hard per se. But yeah. Um, So I think the key idea across all of these problems is that yes, the problem gives you with certain things, but you need to think more. Like think about what is ideal for you in terms of um how how can I make like sort of visual thinking? How can I make my task simpler? Like okay, what if this had happened? Then would it be any easier for me? And if it was, then what stops me from going to something like that? If nothing stops you, then like go for it. So that is my idea. Um yeah, I think these were the main examples I had for today. So now we can just do some random cool problems which are also along similar lines. I myself, which year this is from the 2017. So we can either do some puzzle type problems or we can do some Olympiad type problems. What would people prefer? Both of them are like all of them are like very cool and fun. But what do people prefer? Okay, so we'll do one puzzle first, then maybe we can do one Olympiad problem. This one is a little less like all the problems we did till now were of a very similar theme where you're kind of breaking rules and stuff. This one is more about just usual stuff, but it's still very fun and cool. Okay, so you have 10 prisoners. At first glance, you might already think this is well known or something, but okay, it's not that well. Um, Each of those 10 people is wearing a hat, and there are 10 colors of these hats. But you can see everyone else's hat. So for example, okay, the 10 colors, let's say, are 1, 2, 3, 4 till 10, and the person's people are like P1, P2 till P10. Now each person can get any of the colors. So it's possible everyone gets the same color, it's possible everyone gets a different color, anything is possible. And person one can see everyone else's hat, they can't see their own hat. Um, and now everyone makes a guess on what their own hat's color is. And you want that at least one of them gets it right.
Like, do they guess together or one by one?
Yes, yes, they guess together. They can discuss a strategy beforehand, before they get their hats. But of course, once they get their hats, they have to individually and together guess um, their answers. And it's very weird because, like, how is seeing other people's hats going to give you any information about your own hat color? Like, you're just making a random guess. So, like, yes, there's 10% probability you get it right. But then, I mean, what about the 90% that you don't? What about the like 9 by 10 raised to 10 chance that nobody gets it right if everyone just guesses a random number? So there has to be some sort of strategy
One thing
that,
can be like I'm thinking like first prisoner sees the second prisoner, and suppose the second prisoner is wearing a red hat. So the
okay,
first prisoner says red, then
okay.
the second prisoner sees the third prisoner's hat, and suppose it's yellow. So the second prisoner says yellow, and they complete this circle, and there might be like they
Yeah,
may have.
that's a very good idea. The only problem is what if all 10 are wearing different colors? Then this is guaranteed to fail, right? Because you're going to guess someone else's color, which is going to be different from your own color. But that's a very interesting idea, which is that at least you're trying to use the other people's information in some sort of useful way. We just have to do it slightly differently because we have to take that scenario into account that everyone is wearing a different color. So an interesting question actually is what happens when 10 is replaced by 2. So in both places. So now there are only two colors for the hat, and there are only two people. And you get to see the other person's hat, not your own. This is slightly more well known. So maybe some of you might have seen it, but maybe not. Even this, in fact, is like non-trivial. Like, how do you even do this? Like, all you see is the other person's hat. How are you supposed to guess your own hat?
How many guesses are allowed per prisoner?
Only one. Like, I mean, if there were two guesses, like, then sure, like you can guess both. But each person can guess one for like person one can make a guess of, let's say, my hat color is two. Person two makes a guess that their hat color is also two. Let's say that's possible. But at least one should get it right. Okay, the only trivial case is when there's only one person and one hat. Then of course you can do it because I mean, yes, my hat color is one. As soon as like there are multiple people, it's already very confusing. They can decide upon a certain sequence such that they can't share their guess. No, they can't. I mean, they have to decide it beforehand. Any discussion that has to happen before the hats are assigned. They can decide upon a certain sequence such that P2 comes before P3, thus P2 tells the color. No, 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 but the point is that each of them decides, makes their guess together. So you cannot like wait for someone else's guess. Otherwise, like person one can just guess person two's color, and then person two just knew that okay, whatever person one says is my answer. So then yes, you could do it. But the point is that everyone has to guess simultaneously.
Very bad guess for the answer. be that they might decide that okay, one person's hat, and they can like 9 people say this is the color, and the 10th person then can say like
No, but the point is again that, I mean, for example, like let's say everyone sees person 10's hat and everyone guesses that. So if person 10 got to wait and hear this out, then sure he would have answered. But because you're all doing it simultaneously, like now person 10 can't like use that information. Like only information he can use is something that was discussed beforehand or something that he can see in the hats of person 1 to person 9. Yeah, this is a sort of a well-known sort of problem, but it's like that sort of, it's like those musical pieces which you've heard in those hotels, but like you don't remember them as such like anymore. Um, yeah. That is actually ridiculously cool. The one which is about axiom of choice. That's insane, like that problem. But this is more like this doesn't require axiom of choice, so I think that's okay. Um, yeah, but the funny thing is, none of you have still solved this two people. Like, how hard can it be? Come on. And of course, it's not trivial. So, in fact, this funny story is the first time I heard this is at like IMOTC or something. Someone was telling me this. I was like, no way, that's real. And like, they were like, no, it's real. Like, try it, try it. I was like, he's just trying to scam me. I'm not even going to try this. Then he told me the solution, and I was like, wow, I spoiled myself on such a great problem. But yeah. Yeah, there's also this green eyes riddle, yes, where you get to see everyone else's eyes. But there are only like two types of eye colors or something like that, I think. Here there are like 100, if there are 100 people. Yeah, so
So like
hmm.
one person guesses the opposite of the other person's color and one person guesses the same thing.
Exactly. That solves the problem. So that's very cool. So for example, if both of them had the same number, either 1, 1 and 2, 2, then what they could do is each of them could guess, sorry, let's say person 1 always guesses the same as what they see of person 2. So then in either of these two scenarios, person 1 would have guessed correctly. And person 2, what they'll do is they'll guess the opposite of what person 1 sees. So, okay, basically, like for example, person 1 sees a hat color, they guess the same hat color. Person 2 sees a hat color, they guess the opposite hat color. Does that make sense? So, if they have 1, 2, or 2, 1, then person 2 will guess correctly because they will guess opposite of this person, which is their own. And if they're the same, then person 1 guesses correctly because, yeah. And yeah, once you see it, like you can't unsee this, like of course. But it's not something that's obvious by any stretch of imagination. Um, but it's still very unclear on how this could ever generalize to like so many people. Um, but oh, you didn't get that. Okay, I'll explain again. So I'll just write it down. Person one, so person one can see person two's hat, right? And person two can see person one's hat. So person one guesses same as what he sees for person two. And person two guesses opposite of person one. So person one will guess correctly if and only if both of them were wearing the same hat color, which is these two cases, 1, 1 and 2, 2. So in these two cases, like person one will guess correctly. And in the other two cases, person two will guess correctly because they guessed opposite of what the first person is wearing. So in any of the four cases, like two square cases, at least one of them guesses correctly. Does it make more sense now? Think about it for a bit, like if it's not making sense. And yeah, for people who do understand, like try to think about how this can work for 3 people or for 10 people. Maybe 3 people for starters. What does opposite mean? So like you can see the other person's hat color, right? Like let's say the other person is wearing hat 2. Then I will guess hat 1. The opposite of 2 is 1, opposite of 1 is 2. That's what I meant. Like 3 minus x, if you want more math way of saying that. But like, for example, if person 2 sees that person 1 is wearing 1, I will guess 2. If person 1 is wearing 2, I will guess 1. Cool. Um, yeah, and because there are only two hat colors, I can say opposite. As soon as there are three, now opposite stops making sense. But same still makes sense, somewhat. But okay, now there are two other people. So how do you say same as like what? Both of them? But what if both of them were already very different? It's very unclear. So yeah, I think this was like a problem worth thinking about. Like I just don't want to spoil this at all. Um, all I'll say is like maybe try three, although I would say three is as hard as 10. If you solve three, you solve 10. If you solve 10, you solve three. Um, so maybe it's not very useful to think of three, but it's still a little bit more convenient.
Okay, so what if we do? I'm not exactly sure if this would work,
Mhm.
but like this, the second person in the 10th case, the second
Okay.
person will get first person's number,
Okay.
and after that, every I is going to guess the I plus one number until like until 10, and then the first person will guess if all of the others have different colors, and the first person is going to guess the same thing. The other
The
color.
last remaining color you mean.
Yes.
Interesting. Uh, so you're saying person two guesses person one. Okay, so what if I construct something like um okay. So wait, this is interesting. Okay, but
Okay.
you could always have something like 1 2 1 2 3, right?
It misses the case when person 2 and person 3 are the same color, I think.
Hmm.
Yes.
Yeah, I think like if these two are the same, like it could even be just 1 2 1 2 1 2 1 2. Like in that case, you're kind of like stuck. Because what you're saying is that each person guesses the one before them, except person one, who, if all others are distinct, then okay, but maybe you can add in a clause that if others are like 2 1 2 1 2 1, then I guess one or something. But it's going to be messy. Yeah. And even that is not guaranteed. Like, I mean, I can just make this one 7, for example, to make it even more random.
Yes.
So, but yeah, it's a cool idea. And it's in some way trying to generalize the same thing we tried here, but um, it's a lot more, like too many possibilities to handle. So actually, yeah, let's think of three. Even though I think it doesn't really make the problem much easier, it's just easier to like write and stuff for me. So like you have three people and three head colors, and you get to see the other two people's head colors. The interesting thing actually about this is that you have a 1/3 percentage of getting it right. Like, I mean, each person individually. Like, yes, I mean, you can have a strategy. So these are not independent events, if you know what that term means. But the point is that okay, I'll probably not go into this, but for people who are like interested, like the interesting thing is that each person's probability of getting it right is 1/3. And all of these add up to one. So a way of thinking about it is that like probability of A union B union C. Okay, this is not relevant to solving the problem, by the way, but is equal to like is rather I'll say um at least or at most. At most. At most probability of A plus probability of B plus probability of C, right? Like I mean probability of a union is at most sum of the individual probabilities. And the interesting thing is that the sum is actually at most like this is one. And you need probability of A union B union C, the fact that at least one of them gets it right, to be exactly one. So you kind of need some sort of strange like equalities, like no intersections in some sense. But okay, I mean that also can give you some intuition, by the way, but I think that's a bit like far-fetched. Like let's think of this more simply. Um, So maybe we'll go back to our two people and try to think of this in a different way. Like, yes, we thought of it in 1 and 2. First of all, let's replace 1 and 2 with 1 and 0 because, I mean, binary. Of course, the actual solution is not going to be with binary because, of course, 10 numbers. But, um, like, what do you think is interesting about like these blocks? Like, yes, they're opposite and these are same, but another way of thinking about this is that the sum of these numbers is 0 mod 2, and the sum of these numbers is 1 mod 2. Like these two, in this set, they add up to an odd. In this set, they add up to an even. And this is a big hint, actually. Um, and person 1 gets it right if and only if the sum is 0 mod 2. Person 2 gets it right if and only if the sum is 1 mod 2. So what do you think? Like, could we construct a way so that person
Yeah.
1 gets it right if and only if it's like 1 mod 3 sum? If person 2 gets it right, then it's 2 mod 3. Someone has an idea?
Yeah, it's done, right? You just calculate the sum of the others and yes, accordingly.
Exactly. Exactly. So everyone makes a guess on what the total sum is. Like person 1 guesses that the total sum is 1 mod 3. And on the basis of that, they make their guess because they know person 2 and person 3's had numbers. So let's say they see 2 and 1. So these two add up to like 0 mod 3. And then they have guessed that the total sum is 1. So that means that they must have themselves been wearing 1. And of course, they mean their initial guess of 1 may not have been right. But at least one of these guys is going to make a good guess, right? At least one of them is going to guess the sum of numbers correctly because modulo 3, there are only 3 possibilities. Okay, this should be 0, but whatever. Um, so the idea is that each person makes their own individual guess. And this is decided beforehand that, okay, I will assume that the sum is 1 mod 3. He will assume that it's 2 mod 3. She will assume it's 3 mod 3, etc. And on the basis of that, they can see everyone else's, so they can make their own guess because there's exactly one thing which will make the total sum work out, and therefore one of them will get it right. And interestingly, exactly one of them will get it right. So, and yeah, the exact same idea generalizes for 10 numbers because now you look at it modulo 10. Boom. So, yeah, okay, maybe I spoiled it a bit too much with this idea, but yeah, this is very cool problem. We have a couple of minutes, so I guess it's not enough to do a math problem, but I mean, okay, these are math problems, but it's not enough to do an actual Olympiad problem. So we can do one more puzzle. This was not the plan for today, but it's okay. Puzzles are fun. We have it. I'll have to find one of my. Okay, we can also, by the way, try the one I had given at like the start of the class, which we didn't discuss that time. Uh, this. But I think someone said they've seen this, but I think most people wouldn't have, I guess. I mean, maybe it's famous, but not to my knowledge. Like I've seen it only in like some random Canada handout apart from the Oxford MET. But and also this is like not technically from like it's based on a problem I found there. Like it's that is a reasonably different problem, but the idea is similar. So yeah, the problem basically says is that again you have, people are wearing some sense hats, but now each hat can have like infinitely many possibilities, like 1 to infinity, anything. Um, the only condition is that the numbers on your foreheads differ by 1, so they're consecutive numbers in some order. Either the first person is greater than by 1 or the second person is greater by 1. And okay, they're natural numbers, um, positive integers. So yeah, this is interesting because Alice starts, okay, I don't know my number. Bob says, I don't know my number either. Alice says, I still don't know my number. But then Bob says, I know my number now. Like, that's crazy. Suddenly, like, they figured out their number, even though it could have been bigger or smaller. So, like, what is even going on? Like, how did the person not know their number, but then like Just by hearing the fact that the other guy doesn't know that number, they figured out their number. Like that's magic. And that really tells you how you want to like look for information. In terms of like um, how do you gain information from these statements? Like these statements are telling you something about the numbers, but what is it that they're telling? Alice's number is one. Um, that's not the answer, but that's an interesting guess. So let's actually think about it. Like, let's say Alice's number is one. The interesting thing is that Bob's number cannot be zero, of course, because it's a positive integer. So it has to be two. So if Bob sees that Alice's number is one, then Bob will just know that his number is two. But the thing is, Bob started by saying, I don't know my number. So if Bob just saw one is written on Alice's head, Bob would just say, I know my number. But Bob said that they don't know their number. But later on, they said that they know the number. So that's very interesting.
Bob's number will be 1.
If Bob's number was one, then Alice's number is supposed to be two. So Alice on the first round itself would have said, I know my number. It's two.
So we continue like the 2.
Yeah. That's sort of the idea. How do you continue? Like, okay. So let's think about it like this, right? Alice says that they don't know their number. The information that gives us is that Bob's number is not one. Because if Bob's number was one, then Alice would just know that the number is two. So now we know that Bob's number is at least two. And okay, Alice's number we don't know much. But then Bob says they don't know Alice's number. So we know now that Alice's number is also at least two. And then we can repeat this until so okay, let's actually solve the more general problem where they keep saying I don't know my number until eventually after like some 100 turns, finally Bob says I know my number. So the interesting thing is now once both of their numbers are at least two, if Alice saw that this guy's number is exactly two, then Alice knows that okay, my number can't have been one because I know that my number is at least two. So it has to be three. So now you know that each number is going to be at least three. And then you can repeat this. And then eventually they'll figure out their number because eventually you will get at least Bob's number. At which point there'll be only one possibility. So that's the idea. Okay, I think time's close to up. I don't have much more. I guess I do have more puzzles, but I think now people would have got bored of these puzzles. Instead, if people have doubts about like anything, they can ask now.
I wanted to ask, like, is there a solution set to the Sophie problems?
So yeah, I think most probably there will be, which we will also like send across. It might take a while, like because we're all also preparing for IMOTC and all those things. So many of us are like a little busy. But definitely we will in fact we were even thinking we can have like common mistakes and stuff like that uploaded, but I can't really give any guarantee on by when per se, but we'll definitely try to do it.
Okay.
Anyone else, any questions about Sophie? Also, yes, you can ask because like you can ask. um yeah, also maybe I'll stop recording.